Okay, guys. So we had an earlier video today. Oh, my hair's crazy. About applications of trigonometric functions. So we're going to continue on with that with two word problems here. And so when I share the screen, what I'd ask you to do is pause the video and see if you can answer these on your own, and then maybe continue the video after that. So try to set them up as you would. They're two separate questions. So one's about a grasshopper named Gary, and then Jessica. So let's see how we do here. So pause the video and maybe see how that works out for you. Okay, so I'm going to just edit this a bit and move that down there. And I'm going to turn off my video here. And okay, so let's sort of pick this bit apart here, and we can. Okay, so let's sketch the diagram here first. So, so we've got a wheel. So I guess the easiest thing here would be to. All right. Technical problems here. Oh, there we go. Let's draw a wheel. Oh my goodness. Okay, so we got a wheel. Okay, and I guess that wheel is like sitting on the road. So, and what do we know about the wheel? Well, it takes 1.2. No, sorry. Scroll up here. It takes 4 seconds to go around. So to do a full turn is 4 seconds, and the wheel has a diameter of 3 feet. Pretty big wheel, 3 feet across. And so this question is a little bit easier than what we did earlier with the Ferris wheel, because the ground is actually at 0. So the bottom of the wheel would be at 0, top of the wheel is at 3, and the middle of the wheel, where the hub would be 1.5. So I'm going to sketch a sine curve or sinusoidal curve for this. And I'm just going to draw a real rough shape here. And I'm going to make the ground a height of 0 here. And so the top of the wheel would have a maximum height of 3, and the middle of the wheel would be 1.5. And it has a 4-second period. So the 4 quadrants then, I guess, would go from 1, 2, 3, 4. So the graph's not terribly accurate. My spacing's not the best here, but it'll do. Okay, so where does the grasshopper get on? So Gary the grasshopper, I don't know. That's my grasshopper. So it gets on, let's see, jumps on the top of the wheel. So it gets on here, and then would start to rotate in a downward direction. And in this question, it really wouldn't matter which way the wheel rotated, because if it went to the left, it would go down. If it went to the right, it would go down. So what do I know? Well, I know Gary starts at 3 meters above the ground, and then after 4 seconds should be back at 3 feet above the ground. And of course, after 2 seconds, he'd be at the bottom of the ground. And then at 1 second, 1.5, and at 3 seconds, 1.5 also. So the shape of the curve would look something like that, okay? And I can find out all the properties here. I could say, well, the amplitude is 1.5. The period is 4 seconds. And the midline is at y equals 1.5. And my phase shift, once again, it kind of depends on whether I'm looking at sine or cos here. So when I look at this, the first thing I sort of see, I guess, in terms of the two main functions is a cos curve, and it's a non-flipped cos curve. So I think I would start with cosine first. So So question A asks us to write a sine and cosine equation. Well, let's do the cosine equation. So it's going to be y equals, now the amplitude is 1.5, so the A value would be 1.5. And notice it's positive here, not negative, because you're starting at a high point and then rotating downwards. Cos. Now my B value, to get B, that's 2 pi over the period, and the period is 4. So my B value should be pi over 2. So pi over 2 x, and then plus the D value of 1.5. And probably the main reason I didn't see a sine graph here is I have to phase shift to give me a sine graph. Now, if I want to use function notation, if you're going into calculus after this, you might see the function written as this, where you're actually relating the height versus time. So using h for height, or h of t for height, and t for time. But if you want to write just with x's and y's, that's okay. But you'd have to remember that the y-axis is the height, and that the x-axis is actually measuring time in this question. So if I want to write a sine equation, I guess I could look at a sine. Now the sine always starts on the midline. And so you'd want to find a point that's on the midline. So you could pick that as your start point, the one at 1 second, or you could pick the one at 3 seconds. If I pick the one at 1 second, that's an inverted sine. So I could just say that's going to be negative 1.5 A value, sine, same period, so same B value, pi over 2, and then maybe x minus 1, went to the right by 1. Plus 1.5, or if you want to, you could say 1.5 sine pi over 2 x minus 3. And if you really want it to be clever, the graph would go down here, and that would be negative 1. So you could say it's also 1.5 sine pi over 2, and now it'd be x plus 1, move to the left 1, plus 1.5. And so all 4 of those functions would work for us here, okay? So I'm gonna need to move this down. Okay. And so there's our equations there. So question B, what did question B want? Question B asked us to determine Gary's height after 1.2 seconds and 1 hour. So let's write that on the margin here, 1.2 seconds and 1 hour. Now, you could use any of these formulas or some other formula if you want to create. But what I find useful is always picking the one with no phase shift. So in this case, I would pick the cosine equation to work with here. I'm going to plug in some numbers. So let's say y equals 1.5 cosine of pi over 2 times 1.2 plus 1.5. Now for entering this on your calculator, I would put 1.5 cos, and what I would do here is this 1.2 is actually over 1. So this is really 1.2 pi divided by 2. So this pi over 2 times times 1.2 over 1 would be 1.2 pi over 2. And I guess you could divide that and be 0.6 pi if you want, and then plus 1.5. And so I want to make sure that I'm on or in radian mode here. So if you want to type that in, I would say 1.5 cosine bracket 1.2 pi divided by 2, close my bracket, plus 1.5. And I should get a height of, where is it here, 1.04. We'll always round it to 2 decimal places, 1.04 feet. So first of all, I'm gonna look at my graph and see if that even seems close on the graph. So at 1.2 seconds, I'm gonna be about here. If I go up to here, I go across, that seems reasonable, 1.04. So it's not over 1.5. So I think that's looks like a pretty solid answer there. Now the second question said 1 hour, And you could just use the formula. There's actually a little trick on this one. I'll show you in a bit. But I'll use a different color here. Let's use blue for this one. So now you say y is equal to 1.5 cos. And now I'm going to enter 1 hour. But of course, 1 hour is 60 minutes. And every minute is 60 seconds. So that's going to be 60 times 60, which is 3,600 pi. Divide by 2, close the bracket, plus 1.5. And so if I punch those numbers in, 1.5 cos of bracket 3,600 pi, divide by 2, and then add 1.5, and I'm getting a height of 3. So 3 feet. Okay, so the little trick you could do here is if you go back to the graph, notice that at 4 seconds, you're back at the maximum height of 3. So after 8 seconds, you'd be back at the maximum height of 3, after 12 seconds, and so on and so on. So if you actually take 1 minute, let's say 60 seconds, and you divide it by 4, because it's 4 seconds to do a period, that would actually give you 15 periods. That'd be 1 minute. And if you wanted to go for an hour, you would times that by 60. So really, it would be 900 periods away, but it would really be at the same height as 4 seconds would be, or even as 0 seconds would be. So you could just use the sort of the symmetry of the graph to do that. Okay, question C. Question C is a bit more complicated. Question C says, determine the height for Gary to reach a height of 0.5 meters above the ground for the first time and for the second time. So I'm going to set up an equation here, and once again using the equation I use in question B. So I want a height of 0.5, right? 0.5, yeah. Actually, I did make a mistake with this question right up here. I wouldn't be cruel to you like this. I would have said 0.5 feet. I wouldn't alter the feet and the meters and have you do some kind of weird conversion. How many miles is it here? So let's go 0.5 feet. And that equals 1.5 cosine pi over 2x plus 1.5. Okay, so this really is, where are we here? Bring over the 1.5, so I'm going to subtract 1.5 from both sides. So that's going to give me -1 equals 1.5 cosine. And I'm going to turn this pi over 2 into a here. So let's say let a equal pi over 2x. And in doing this, I basically just turn into a basic trig equation. So -1 over 1.5 equals the cosine of a. And I'm going to space a bit more here. Get a bit of room to work. Okay, so need to find out where this angle could be here. So we know that cosine is negative in quadrants 2 and in quadrant 3. Now I'm going to calculate both of these angles, angle A1 and angle A2. But I'm going to show you that if you just find angle A1, you can actually use the symmetry of the graph to get angle A2 much quicker than calculating it out. But let's just sort of show you how we do this here. So what I'm interested in is these two triangles that would have the same reference angle in both. So this would be -1 for x, because that's the x value over the r value, and a radius of 1.5. So the negative number really isn't important other than it tells you which quadrants you're in here. So I'm going to look for my reference angle. Let's find our reference angle. So to find the reference angle, I go second function cos of +1 divided by 1.5. So notice I'm not using the negative here because I don't really need to know that right now. I just want to know what the reference angle would be. So, second function cos of 1 divided by 1.5, and that gives me an answer of, so reference angle equal to 0.8411 roughly. And that's the angle here, green angle, and that green angle there. So the first angle, I'm going to call that A1, as we said. Angle A1 would be equal to pi minus the reference angle. And angle A2 would equal pi plus the reference angle. Okay, so let's do pi, second function pi minus that number. And I get A1 equaling 2.3005. And then I'm just going to calculate that again. 1 divided by 1.5. So I get 0.4. So now I go pi plus that number. And I get a value of, for angle A2, equal to 3.983. Now these numbers are in radians because they're just looking at where you are on the graph. So you have to remember this little let statement you used here, or that I used here. So I'm going to make that pi over 2 equals this number, and pi over 2x equals this number. Let's call this x2 and x1 here. Okay, so once again, let's move that other question down a bit further. A lot of writing here. Okay. Okie dokie. Why can't I scroll here? There we go. Okay, so let's take 2 point, I'll do this one because this is on my calculator already. Let's do x2. So 3.98222. Let's times it by 2 and divide it by pi. So I get x2 being 2.535 approximately. And now if I use 2.3005 times that by 2 and divide that by pi. And I get 1.464. And once again, I'm going to talk about how you can use symmetry here for this, but let's just sort of see if that matches our graph here. So I'm just going to shrink this down a bit. So let's erase this now. So 1.46 would be about here. And so that seems to be roughly 0.5 on the graph. And then 2.5 would be here. Okay, so what I wanted to show you was if I zoom in, so let's remember these two numbers here. So if you have those two numbers written, and I'm going to go back to the graph here. So over here, I'm going to write 1.46 roughly and 2.54 approximately. Okay. So let's just sort of zoom in here. Okay, so let's see if we can use symmetry here to get this value. Okay, so if you had just worked out the first value of 1.46, that means that when we look for 0.5 as our height, we'll go across here. That means that value right there is 1.46. Okay. Now, the graph should be symmetrical in that the distance from this high point to that point there should be the same as it would be from this point to that point up there. So I don't know if you can see that, but the symmetry from the high point to where it is at 0.5 would have to be the same as where it is here. And of course, that should make sense because on the circle, if you're at a height here, the distance here, that distance there, would be the same as the distance to this sort of high point over here. So if you know the first number is 1.46, then to get this number, you just have to go to the end of the period, which is 4 seconds, and minus 1.46. And if you do that, you get that number there. So that's probably a quicker way to get the second value for you here. So what was the question asking? Let's go back to the question. So the question says, determine the time Gary's at a height of 0.5 feet above the ground for the first time. Well, that actually would be the very first number. So down here, the very first time So the first time would be 1.46 seconds. Now, the second part of that question is actually a little bit trickier here, which says for the 22nd time. So really this point here would be the first time, and then this point here would be the second time. So we're going to have to do a few more periods here, and I'm going to run out of room if I do this, because even if I just do one more period, this would be the third time, and over here that would be the fourth time. And so that would mean basically I have to add a bunch of periods here. So what I'm going to look at here is it says 22nd time, which would be an even number of periods. So it would have to be related to the second time. And of course, if I go over here, that would be the fourth time, and I have to add one period. So let's go down here, and I'm going to say for the second time, so for t2, actually let's do it this way. Just draw a line here, separate the question. So for the second time, it would take 2.535 seconds. And then I'd have to add one period to get to the fourth time. And I'd have to add another period to get to the sixth time. And what I want to know is when I go all the way to the 22nd time, how many periods would I actually have to add here? Well, you could think of it this way, I guess, is that this would be T1, this would be T2, this would be T3, and T4 would be the 8th time. So you can actually times the term number by 2, or you could take the second time divided by 2, fourth term divided by 2, sixth time divided by 2, 22nd time divided by 2, which would be T11. So notice to go from the first to the second time, that was one period. To go from the first to the third, that would be 2 periods. So I'm going to have to add 10 periods. So my time was 2.535, and now I have to add 10 periods, but each period is 4 seconds. So it's going to be 40 plus that number, which would be 42.53, I think, roughly, or maybe 54 seconds. Yeah, I think that's right. Let me just double check that, make sure I'm doing that right. So yeah, because it'd be 10, so 10 times 4, then I have to add the period, so plus 2.53, so approximately 42.53 seconds. Okay, so our next question here, not maybe as many steps to it, but still kind of a tricky question. So we've got a wheel here, and it's just kind of a silly question, but so we have this wheel, and the bottom of the wheel is actually submerged in water. Boy, I'm having a hard time getting rid of that. There we go. So we've got this water, and it's submerged in water in such a way that the maximum depth, it says, is 4 meters below. So the maximum depth is 4 meters. So basically this here is, or 4 feet, sorry, 4 feet below. Okay, and we know that the diameter of the wheel is 20 feet. So basically from here to here is 20 feet. And to do a single rotation, to go all the way around, is 30 seconds. Okay, so I'm going to start off by trying to sketch this curve. And it wants us to write the equations for the sine and cosine relative to the surface of the water. So I'm going to make the water 0 here. So the maximum depth is 4. So we're going to be at -4 at the bottom. And of course, the wheel is 20 feet, diameter of 20 feet. So 20 plus -4 would be 16. And in the middle, wherever the middle is here, it would have to be, well, let's think here. If the diameter is 20, the radius equals 10 feet, which means this distance from here to here, that would have to be 6 feet. So this would have to be 6 here. And of course, going from here to here would be another 10 feet here. Okay, so where do we start though? So I mean, maybe my four quadrants here. Okay, now be careful, this line here is not the midline, that's the surface of the water. So I want to be careful when I plug my points in here. So where does Jessica get on the wheel? And then I guess, how does it rotate here? So it says that Jessica, where is it? It starts her training attached to the side at a height of 6. She's going to start right on the midline, looks like, above the water. So maybe she's starting here. But she could start on the other side. But what's important next is that when the wheel rotates, she moves downwards. So she's going to go downwards first and into the water. So she's going to start at a height of 6. She's going to go downwards. And then basically after the period, she should be back to where she started from again. So what is the period here? Well, the period to go around the wheel is 30 seconds. So she's got a pretty slow rotating wheel here. So this would be 30. This would be 15. This would be 7.5. And this would be 22.5 here. So because the wheel rotates down, she's going to go from a midpoint to a low point, back to a midpoint, up to a high point, and then back to the midpoint. So the graph's going to look something like that. So when I look at that graph, I'm definitely seeing a sign that's been flipped here. So I'm going to start off with sine, but let's find some properties here. The amplitude is 10. That's the radius of the circle. The period is 30 seconds. The phase shift is, well, it depends what I look at. If it's sine, I don't see any phase shift here. And then midline would be y is equal to 6, I guess. So if I write an equation for sine, first of all, I would say y, ooh, that's crazy. Let's undo that. So I'm going to write an equation for sine. Now, because it's starting at the midline going down, it's a negative sine graph. So I'm going to say negative a, so negative 10 sine. Now my b value is 2 pi over the period of 30. So it'd be pi over 15. Okay, so pi over 15. And I'm choosing sine because there's no phase shift if I think of that. And I go plus the midline. So don't say minus 4. You want to say plus 6 here. Okay, so that's where our midline would be here. And what next? Okay, we're at a cosine equation. So we're at cosine. So y is equal to, well, if it's cosine, it has to start up high or down low. So I could use that as my start point, or I could use that as my start point. So if I use the first one at 7.5, that's a negative cos. So negative 10 cosine pi over 15 x. Now I'm going to the right, so minus 7.5 bracket, and then same midline. If I use the high point at 22.5, you take a positive 10 cos pi over 15, but now I have to go x minus 22.5, close the bracket, plus 6 here. Now, to answer any kind of mathematical question, I'm going to use the sine equation because it's just easier without the phase shift. So let's do that then. Okay, so what was the question asking in the first place? So it says, if her parents keep Jessica on the wheel for 5 rotations, how long must she hold her breath? Well, Jessica is terrestrial, so she cannot breathe when she's in the water. So anytime she's below a height of 0, she's going to have to hold her breath. So what I'm going to try to find out are these x-intercepts here. I'm going to try to find out that place and that place. And we're going to use that little technique we used above if we just find one of them. But this point here, I'm going to say that's time 1. And I'm going to say this here is time 2. So before I calculate it, let's just say that, let's just say time 1 was 1 second. It's not going to be 1 second. And let's say time 2 was 14 seconds. Just using easy numbers to work with here. And so the first time she enters the water was 1 second, just pretending. and that she comes out of the water at 14 seconds. Well, if she had to hold her breath when she's underwater, then we would do 14 minus 1, which would be 13 seconds. Now, that would be for one rotation of the wheel. If she's on for 5 rotations, I would then times that number by 5. So we have to do a little bit of math here to get to the final answer. But let's actually find out the real values of T1 and T2. So I'm going to make my height 0. So let's make our height 0. And we say -10 sine. And once again, I'm just going to make this some other letter. Let's call it B this time, plus 6. So maybe I'll just make a note of that, that B is equal to pi over 15x. Okay, so let's bring the 6 over. So we get -6 equals -10 sine of B. Divide by -10, so I get 6 over 10. The negatives cancel out, getting the sine of B. And now I could reduce that, I guess, to 3 over 5. Don't really have to, but sine of B. Now at this point here, this is just a solving for what angle, for what quadrant you're in here. So I'm going to use angles in standard position, and I have to figure out where the sine value would be positive. So that would be in quadrant 1 and quadrant 2. So there'd be an angle here and an angle over here. Now, before I find those angles, let's just go back to the diagram. Notice that the first answer is in quadrant 1, and the second answer is in quadrant 2, actually. So it actually does sort of make sense here that we're kind of on the right track to doing this. If I create my reference triangles, what I'm going to try to find is the reference angle for both these, which should be the same number. So I know that the y value here is 3, and this is 3, and that's 5, and that's 5. So really to find the reference angle, I'll just go up here to find my reference angle. I'm going to go second function sine of 3 divided by 5. And this is a bit different than the last question where I had to ignore the negative. This one's not even negative to start with here. So I'm going to go second function sine bracket 3 divided by 5. And that gives me a reference angle of reference angle of 0.6435 radians. So where is that? That's this angle here and that angle there. So angle, let's get these names here. Let's call this, this is angle B1, and this is going to be angle B2. So angle B1 would be equal to 0.6435 because that's in the first quadrant, so that wouldn't change. Angle B2 would be equal to pi minus the reference angle. So that would be equal to pi minus the reference angle of 2.4981 roughly. Okay. Now all I have to do is find the first one, by the way, but I'm going to find both just to make sure you guys believe what I'm saying here. So I'm going to make this x1. So I have to remember that b was really pi x over 15, and that equals 0.6435. And x equals, let's work that out. So it's x1. So the points, let's just do it again, 0.6435 times that by 15, divide it by pi, gives us a value of 3.072 seconds. So I'm going to leave B2 here for a bit. And I'm going to go up to the graph and see if we can just see that from the graph. Okay. So T1 is 3.072 seconds. So it wasn't 1 second. It's that number right there. Now, if I want to use symmetry here for the graph, this distance here, let's see if I can color this in, that distance there should be the same as that distance there. So I'm going to go 15 minus this 3.072. So 15 minus 3.072 makes T2 11.928 approximately. Okay, 928. But let's go back to the calculation below and see if we actually get this number here. So I'm going to say that B2 would be pi x2 over 15 equaling 2.4981. So x2 would be 2.4981 multiplied by 15 and divided by pi. Hot damn, look at that, 11.928. So it does actually give us the two numbers we got up here. So I always find symmetry a bit easier to work with here. So what I'm trying to find out is the time that she has to hold her breath for, which would be the time that she's under the water, that time right there. So I'm going to take 11 seconds minus the 3 seconds. So let's go down here. So I've got 11.928 and I'm minusing 3.072. So minus 3.072, and that would be 8.8555 and a bunch of other numbers after that. Okay, now that is for one rotation. Okay, her parents are super cool, so they're letting her do 5 rotations. So we times this number by 5. So times it by 5, which gives us 44.28 roughly seconds. So it's not actually that long to hold your breath. I'm sure Jessica could probably handle this, because really all she has to do is hold her breath for one interval of 8.9 seconds. So maybe her parents should have slowed the wheel down a bit. But anyway, they probably love her daughter. So anyway, so there's our two questions. So we've got 44.28 seconds, and we've got our two equations right here. Okay, so that's going to be it for tonight. I'm tired, so I'm going to stop the video here. And let's... yeah. Okay, so there we go. So anyways, I hope you guys are doing well, and this will be for tomorrow's lesson. So it's